In this video, we are going to look at the new 2025 OWASP Top 10 together and talk about what's actually going on, in normal language, one risk at a time. Now, an important reminder, your exam does not change just because OWASP does, nor whenever any other framework, law, or technology changes. Your exam changes with the next exam update. All knowledge on it is a point in time, meaning if the certification you are studying for was last updated in 2025, whatever changes after that and before the next exam update is not on the exam. The certification organization will likely update the OWASP curriculum next update they do, but not until then. Most certifications update every 3 to 5 years. The CISSP was in 2024, so it will not get the new OWASP 2025 version until the next update in 2027. The CISM was updated in 2022, and 𝗖𝗓𝗃 normally does 5-year cycles. This time, they are a little early. It is in November 2026. Certified in Cybersecurity was in 2023. Next update is September 2026, so it is getting it soon. Security Plus was in 2023, and we expect it to update in late 2026, so also soon. If you are studying for other certifications, go look up when they last changed and their update cycle. But use the official pages, not random blogs or generative AI. All that said, this is still very exam relevant. Most of the risks are on the exams, just not by the OWASP name. You will be tested on the concept, how it works, what to look out for, how we mitigate, and so on. Now that I got all the disclaimers out of the way, let's look at the new top 10. It is mostly the same list as in 2021, but some things were moved around, removed, or added. So A1 broken access control stays the same at number 1. But with the old SSRF that was at A10 from 2021 merged into it. Security misconfiguration A2 moves up from number 5. A3, or software supply chain failures, is one of the new 2 items, but it does contain some of the old 2021 𝗖𝗚𝗏 vulnerable and outdated components. Cryptographic failures has moved from A2 to A4. Injection is down from A3 to A5. Insecure design also down from A4 in the 2021 version to A6 in 2025. Then authentication failures stays at number 7, same with 8, software or data integrity failures, and A9, security logging and alerting failures, also stays at the same spot. A10 is the only true new entry with mishandling of exceptional conditions. All right, let's look at the actual top 10. We start with A1, and it hasn't moved. Broken access control is still sitting at the top, and for good reason. In the 2025 data, every single tested application had some form of access control problem. Not most of them. All of them. Access control is simply the rules for who can do what, who can see which records, who can change which settings, who can run which actions. When those rules are missing, weak, or implemented in the wrong place, you end up with people seeing and doing things they should never be able to. This can be as simple as changing an ID in the URL and suddenly looking at someone else's account instead of your own. It can be a JSON web token that never expires. It can be a misconfigured course policy that lets any random web page talk to your API as if it were your own front end. And the real danger isn't that it's clever or complex. The danger is that it's everywhere and attackers will find our weakest link and exploit it. If they can guess a URL or tweak a parameter and your system doesn't recheck who this user is and what they're allowed to touch, you're in trouble. So how do we fight this in practice? We deny by default. Nobody gets access to anything unless you explicitly grant it. You centralize access checks in trusted server-side code, not in JavaScript in the browser. You enforce ownership at the data level so users can only see and change their own records. You log failed access attempts and pay attention if someone keeps poking at things they shouldn't reach. And you keep tokens short-lived and easy to invalidate. Zero Trust can fix much of this, not all, but much. If you remember one thing here, it's this. Never trust the client, always recheck permissions on the server, and assume that anything that's not locked down will be tested by an attacker. Number A2 is security misconfiguration, and this one is closely tied to access controls. It used to sit at number 5. It's jumped up because our systems have become incredibly configurable. Cloud platforms, containers, frameworks, managed services, everything has dozens or hundreds of configurable options. And the more options you have, the easier it becomes to leave something in a bad state. Default accounts left active, sample apps still running on production servers, error pages that happily print stack traces and version numbers, cloud storage buckets left public when they were supposed to be private, servers missing security headers, features turned on that nobody actually needs. Misconfiguration by itself is just an open door. But remember how it ties into broken access control. If you leave a storage bucket open to the internet, that's the misconfiguration. The impact comes from the fact that now anyone can read or download data they should never see. That's access control collapsing because the environment was set up wrong. Defending against this is less about a single magic control and more about discipline. You want a repeatable hardening process. Every environment, dev, QA, production, should be built from the same secure baseline with automation, not by hand. You strip away anything you don't use. You keep an eye on patches and security notes. You review cloud permissions regularly. And you test your config the same way you test your code, with tools that can scan and report misconfigurations. We can use secure defaults, where everything is locked down and we only open exactly what we need to function. Think of this one as housekeeping. If you don't intentionally lock things down, the defaults will come back to bite you. Next, we have A3. That is software supply chain failures, and this one has grown far beyond just using components with known vulnerabilities. Today, your application isn't just the code your team wrote, it's also the libraries, frameworks, plugins, build tools, container images, IDE extensions, and the whole CI/CD pipeline that glues everything together. A supply chain failure is when something in that chain is vulnerable or malicious, and you pull it into your environment and trust it. That can be an outdated library with a known critical flaw. It can be a compromised package in a public repository. It can be a build server that's been taken over, so it quietly injects backdoors into your binaries. It can be a wallet extension that behaves normally for everyone, until a very specific high-value target uses it, then it flips. And you're at risk if you don't know exactly which components you're using, including nested dependencies. If you never scan them, if you let developers grab random packages from random websites, if you don't lock down who can change CI/CD configs or promote builds, if one person can commit code and push it all the way into production on their own. The defense here is about visibility and control. You need an accurate software bill of materials for your application, and you need to keep it up to date. You track versions, you monitor for new CVEs against those components, you remove dependencies you no longer use, you pull from trusted signed sources, and you treat your build pipeline as a high-value asset with strong authentication, strict access control, separation of duties, and tamper-evident logs. The bottom line, you're only as secure as the weakest piece of code you trust, including the parts you didn't write. If you're not managing your supply chain deliberately, someone else will manage it for you. A4 is cryptographic failures, and this isn't just about forgetting to turn on HTTPS. It covers everything around how you protect sensitive data in transit and at rest, how you generate and store keys, and which algorithms and modes you pick. We're long past the days where encryption being too slow is a real excuse. Modern CPUs have hardware support for common algorithms. Cloud providers make certificate management easier than it's ever been, and yet we still see weak ciphers, outdated protocols, default keys, hard-coded keys in source code, poor randomness, and broken password storage everywhere. Think about the types of data you really care about. Passwords, credit card numbers, health records, personal details, business secrets. If those end up in plain text on disk, in logs, in backups, or going across the network unencrypted, that's a cryptographic failure. If you use MD5 or SHA-1 for hashing, that's a cryptographic failure. If your password database uses a fast hash with no salt, that's a cryptographic failure. Defending here starts with classification. You need to know which data is sensitive. Then you encrypt it at rest with strong modern algorithms and proper key management. You encrypt everything in transit using TLS with sane settings, and you enforce it. You never store passwords directly. You store hashes using adaptive salted functions like argon2, script, or pbkdf2. And keys themselves need special care. They should be generated with real cryptographic randomness, rotated regularly, and stored in secure modules or cloud key management systems, not in config files in your Git repo. You avoid deprecated algorithms and padding schemes, and you keep an eye on guidance for post-quantum cryptography because some of the crypto we rely on today won't last forever. Much of the data that is stolen today is secure for now. But many of the algorithms we heavily use now are weak against quantum attacks. If the data is important enough, the attackers will just keep it and decrypt it when quantum is practically usable. So we need to change critical data to quantum-safe alternatives now. If you get cryptography wrong, attackers often don't need a clever exploit. They just read what you leaked. So keep crypto boring, modern, and done with trusted libraries and patterns, not custom homegrown designs. Then we have A5, which is injection. It used to be higher, but it's still one of the most tested and most dangerous classes of bugs. If you've ever heard about SQL injection or cross-site scripting, this is where they live. An injection problem shows up anytime untrusted input is mixed with commands or queries in a way that lets the attacker control what gets executed. That can be SQL, NoSQL, OS commands, LDAP, template languages, you name it. The pattern is always the same. Data ends up being treated as code. A classic example is a dynamic SQL query where the application just glues user input directly into the string and sends it to the database. If I can close your string and add my own SQL, I can read or modify data I shouldn't see or even run code on the server. And the defenses here are well known. They just require discipline. Use parameterized queries, prepared statements, or safe APIs that keep the query and the data separate. Validate input on the server side. Escape output in the right way for the right context. And add good security testing into your pipeline so you catch obvious injection issues before they ship. Even with new categories like LLM prompt injection showing up, the core idea hasn't changed. Anytime you let untrusted input shape the logic that runs, you need to stop and ask yourself whether you've drawn a hard line between data and commands. So input sanitation and limitations. Then we have insecure design, A6. And this isn't about writing the code badly, this is about designing the system wrong from the start. You can have a perfect implementation of a bad idea and it'll still be insecure. Insecure design is about missing or ineffective controls that should have been part of the architecture. For example, a password recovery flow that uses knowledge-based questions like, "What's your mother's maiden name?" That's a design flaw, not just a coding mistake. A ticketing system that lets you hold hundreds of seats without payment because nobody thought about abuse, that's a design flaw. A high-demand product page with no protection against bots that instantly buy all the stock, also a design problem. Fixing this means moving security earlier in the lifecycle. You don't wait until you have code to scan. You start with requirements and risk. What data are we handling? How exposed is this system? What goes wrong if someone abuses or automates this flow? You bring in threat modeling for your critical paths, authentication, access control, payment flows, business logic. You define what normal looks like and what failure states you want to avoid. And you build a secure development lifecycle with patterns and reusable components that teams can follow instead of reinventing the wheel every time. The key idea, you can't bolt security on at the end and expect miracles. You design it in, you plan for misuse, and you treat secure design as part of how you build, not a separate extra step. If you are building a house and you build the foundation with bad materials, the entire house is at risk. I hope that analogy helps. At A7 is authentication failures. This is everything that lets an attacker pretend to be someone they're not or stay logged in when they shouldn't. Common problems here are very familiar. Allowing weak or default passwords, not blocking credential stuffing or password spraying, using breached passwords without checking, storing passwords in plain text or with weak hashes. Poor session management where tokens are exposed in URLs, never rotated or never invalidated on logout, and broken multi-factor flows or weak fallbacks that undo the whole benefit of MFA. Attackers know that humans reuse passwords and just increment them. If you have taken any of my courses, you have probably heard about how my mother used to use something like Spring 2026 for her password, and then 3 months later when she had to change it. The next one was just Summer 2026. Her passwords followed the rules, but were very predictable. If an attacker got her passwords from 2025, they could guess her 2026 passwords. Now, if it is not predictable, there are still many other issues it could be. If our system doesn't rate limit or detect weird login patterns, it can be used as a testbed for stolen credentials. If your forgot password flow relies on security questions, that can be abused. If your sessions never time out, anyone who walks up to an unlocked machine can ride the existing session. Defending against this has a few clear pillars. Strong modern password policies based on current standards, not old complexity myths. Longer is better. Multi-factor authentication by default for anything important where possible. Checks against lists of known breached passwords. No default credentials in production, hardened registration and recovery paths that don't leak which accounts exist, and secure server-side session management with proper timeouts and rotation. Anytime you make it easier for users to do the wrong thing with passwords, you're helping the attacker. So you make it easier to do the right thing instead, and you back that up with controls that catch automated attacks early. Now we get to A8, software or data integrity failures. This is about what happens when you trust code, updates, or data without checking that they're genuine and unchanged. Think about plugins loaded from third-party CDNs, auto updates that pull binaries without verifying signatures, or CI pipelines that download artifacts from untrusted locations. If you treat those as trusted just because they arrived, you're opening the door to attackers. Think of both the CIA triad's integrity leg, but also the Parkerian hexad's authenticity. The data might look fine, but we don't know where it came from. How can we trust it? Insecure deserialization also lives here. When you take complex, serialized data from a client, deserialize it on the server, and trust the contents, you're effectively letting the client mess with your objects and state. And if the format can be abused, that can lead to remote code execution or other serious impact. To defend against integrity failures, you validate what you consume. You use digital signatures or similar mechanisms for updates and critical data. You restrict your dependency sources to trusted repositories and, for higher-risk environments, mirror them internally after vetting. You harden your CI/CD pipeline and treat it as critical infrastructure. And you don't blindly deserialize untrusted data without checks. The theme is simple. Don't assume that because something came from inside the system, it's safe. Make integrity and authenticity first-class controls. Not an afterthought. We are almost at the end, I promise. Now we have A9, which is logging and alerting failures. And this one is tricky because you often only notice it after something bad has already happened. If you don't log important security events, you can't investigate what went wrong. If you log but never monitor or alert, you won't spot attacks in progress. If you log too much of the wrong thing and flood your team with noise, the important signals get buried. And if logs are easy to tamper with, attackers can cover their tracks. I think every single corporate job I have had in the last 15 to 20 years, when I started, their monitoring systems always had a ton of red blinking lights. People didn't even look at them anymore. At that point, it is useless. When I asked, but why? The answer was always something like, oh, right. That is whatever server, that is okay, as if that explains anything, or just, yeah. We stopped using it because we got too many false positives. And in my head, I am yelling, well then fix it. This is actually our job. Tweak the system so you don't get false positives and fix whatever is wrong with the server. I mean, we could get rid of the monitoring system, but then we would have no clue when things break or we are attacked. So bad idea. I also think in every place, we eventually did get the monitoring system configured right and servers fixed. But just giving up and ignoring it is something that is really weird to me. Okay, rant over. Back to A9. Some of the practical examples could also be only logging successful logins, but not failures, not logging access control checks, never alerting on suspicious patterns, or leaving logs on a single server with no backups. And on the other side, you can cause problems by logging sensitive data like full credit card numbers or passwords, which should never be written to disk in the first place. Good practices are pretty clear. You decide which events are security relevant and log them with enough context to reconstruct what happened. You protect the integrity of those logs, ship them to a central place that your monitoring tools can understand. Set up playbooks so that when an alert fires, people know what to do. And you keep false positives under control so your SOC doesn't get numb to the noise. Logging and alerting won't stop an attack by themselves, but without them, you're flying blind. And you want to know when any issues are happening and not read about it in the news years later. We log what is important, we have automations that alert us, they are configured right. Very few false positives. If it is critical, maybe we also have the automations take action. Logging is always write protected on servers where most admins have no access. And if we need, then we keep some sort of immutable backup offsite. Finally, we have A10. This one is new for 2025, mishandling of exceptional conditions. It sounds abstract, but it's really about how your software behaves when something unusual happens. Not the happy path when it works like it should. This is the weird edge cases, the errors, the unexpected states. When exceptional conditions aren't prevented, detected, or handled correctly, your system can crash, get stuck in a bad state, or open up vulnerabilities. This can show up as logic bugs, race conditions, resource exhaustion, half-completed transactions, or error messages that leak sensitive details. Think about an upload feature that throws an exception but never frees resources until the server runs out of memory. Or a financial transaction that debits one account, then hits an error before crediting the other and doesn't roll back properly. Or error messages that print full stack traces and database details to the user, which an attacker can then use to make better exploits. Preventing this starts with expecting things to go wrong. You validate inputs early, you handle errors close to where they happen, always log them and do something meaningful with them. Have global exception handlers for anything that slips through. And design your transactions so that if something fails partway through, you roll everything back, not leave the system in a half-finished state. You also set limits. Rate limiting, quotas, and throttling can prevent some exceptional conditions from ever happening at scale. Centralize error handling and make it consistent, so you're not chasing 10 different patterns in one application. The ACID model comes to mind here. Remember, that is atomicity, consistency, isolation, and durability. So a real quick reminder, atomicity is a transaction is all or nothing, so either every step completes or none of it does. Consistency is when a transaction must leave the database in a valid state that still follows all defined rules and constraints. Isolation is transactions should not interfere with each other, so each one behaves as if it is running alone. Durability is once a transaction is committed, the data is permanently saved and will survive crashes or power loss. The idea is simple. The more predictable your behavior is under stress and failure, the harder it is for attackers to weaponize your mistakes. All right, let's recap with some quick mitigations after each topic. A1. Broken access control found in every single tested app. If you don't explicitly deny by default, attackers will find the gaps. Zero trust, default deny, and MFA. A2. Security misconfiguration. The more configurable your systems are, the easier it is to leave something wide open by accident. Secure defaults, hardening. A3. Software supply chain failures. You're only as secure as the weakest thing you trust, including code you didn't write, SBOM, and trusted sources. A4. Cryptographic failures. Weak algorithms, bad key storage, or unencrypted sensitive data means attackers don't need a clever exploit, they just read it. Strong cryptography and proper key management. A5. Injection. Anytime untrusted input gets treated as code or a command, an attacker can control what your system executes. Parameterized queries and input validation. A6. Insecure design. You can perfectly implement a bad idea and still get breached. Security has to be designed in, not bolted on. Threat modeling, secure design. A7. Authentication failures. If we have weak passwords, no MFA, and poor session management, we make it trivially easy for attackers to become someone they're not. MFA, secure sessions, strong passwords. A8. Software and data integrity failures. If you trust updates, packages, or serialized data without verifying they're genuine, you're letting attackers rewrite your system's behavior. We use signatures and integrity validation. A9. Logging and alerting failures. If you're not logging the right things and acting on them, you'll find out about the breach from the news. Centralized logging, tuned alerts, react on the right things. A10. Mishandling of exceptional conditions. When things go wrong and your system doesn't handle it cleanly, attackers will weaponize the mess you left behind. Graceful errors, rollback logic, ACID model. And just like that, we are done with the new 2025 OWASP Top 10. Thank you for being here, and I hope this has helped you understand not just OWASP, but why it is so important for your work and your exam.